Bismillahirrahmanirrahim. Greetings. I intend to upload a series of video lectures about some selected topics in calculus. Now, the first few are designed to build the conceptual foundation of a fundamental theorem of calculus, which bridges the gap between differential and integral calculus. Now, in differential calculus, we deal with rate of change. And the concept of rate and ratio are very fundamental for the science of calculus. Very elementary and very fundamental. Now, what we will do, we use a graph as a pictorial, as a geometry, as a visual aid to help us to set up the corresponding algebraic form of it, the analytical form of it. And then after doing algebraic manipulation, at the end, when we go to the concept of limit, that's what calculus takes over. And with the concept of limit, we dive deep into the midget word, which is the word of infinitesimal. That impossible for man ever to go in that word. Only mathematics can go. And then it brings out for us an explicit function that is derived from the original function. That is the reason we call it derivative function. It's a very fascinating subject. Now, in these lectures, in the first few lectures, I'm going to wave my hand and use some vocabularies that I have not already defined, and just give an overall picture of the subject. And then I'm going to dive deep, and every single of them, I'm going to repeat the same thing again and make it explicit and more clear with corresponding examples. So if you are hearing that for the first time, don't get discouraged. The subject is extremely sweet and very simple in reality. And I will do also, as I said, I repeat myself, I will dive into that and make it bring a lot of examples of, so that it becomes very, very kind of comprehensible in a sense. Now, if the time permits, at the end I also say a few words about the history of this subject. So before I start officially for today's lecture and also put them on the bulletin board, I don't have access to blackboard or a whiteboard, sorry about that. But I say a few words aside about ratio and rate. And then I stay out of way and put them on the bulletin board. Okay, then let me say a few words aside, as I mentioned. Ratio and rate, they are in a sense same, they are different. Ratio is, both of them are comparison of two quantities. But in ratio, the quantities that are being compared, they have same units. So the units, they cancel each other. In other words, every single rational number is a ratio. All right? Now, on the other hand, the rate is also comparison of two quantities, but with different units. An example that we are very familiar with, like 50 miles per hour, is comparing, we cannot compare mile and hour, there are two different things. They have different units. But when we are discussing them in calculus, we drop the requirement of the units. Because with rate, the units must be attached to them. But when we are discussing them, we just ignore them in a sense, but the context is saying what we are doing, and we use the word ratio, which in reality is a rate. Okay, then let me say, as I already said a few words aside about also ratio, the relation of them, and then put them on the bulletin board. So that was an overall picture of that. So let me zoom this one and put the material on the board for you. May I do that, please? Thank you. Excuse me, I have to put this one up first to see if it is focused, if it is zoomed correctly. Okay, I suppose it's good, huh? So let me stay out of the way. Now, I talk about ratio, I apologize for the 1,000 times for the primitive equipment I have. Now, here I already mentioned about difference a difference between both rate and ratio. Here, the ratio of, we call it rise over run, we call it a slope of this line. So please do not mix this one. I'm not talking about a right triangle, Pythagorean of a right triangle, the relation between them. I'm not talking about that, don't confuse that. I'm using this triangle, which is a right triangle, as a kind of pictorial, as a visual aid to see the relation between the rise and run in a sense. Now, the ratio of this to this, again I repeat myself, I'm not talking about the length of this, but the numerical value. The numerical value of this over this is the slope of this line. It's not the length of this line, but it's the slope of this line. So again, the ratio of this over this is the slope of this line. That means the slope of this line times this, that we call it run, is equal to rise. You follow me so far? I just put it this one. This is rise over run, then equal to a slope. Then a slope times run will be equal to what? To run. So this picture can give us a good, to remember that as a pictorial kind of reminder to us. So again, the slope of this one, which is a slope, this times this is equal to the what? To the rise. Okay, then this you can take you can pause if you are not following, and take a note or whatever you have interested in. Okay, let me go now to the next one. To the next one is, I guess I go for this one if I may. Now I'm going to repeating the same thing again. Suppose this is the graph of some kind of function. So here I give some value for that, let's say x, but let's say for example 5, I give it to that. If it is y equals to x squared, he gives me 25. Then I give you a little bit more, let's say instead of 5, I get 6. I get what? A square of is 36. So 36 minus 25 is this, we call it what? We call it change. This delta y means change of y. So it's not two variable, because for the beginner of students, they always think about being two variable, and it is in reality two letters of alphabet. Delta is a Greek alphabet, and the y is one of our alphabet. But when we said this stands for change of y, so read delta as a change. So say change of y, and this one delta x, keep it in your mind, call it as a change of x. All right? Now, the difference of them, the difference of when we, I give, for example, x bar, he give me one f of x bar. The function give me some, because function has input and output. If my input is x bar, the output will be f of x bar. Then I go to the next point, some unit more, that I call it delta x, and that will be x1, in this case x1 plus delta x. I give it to the function as an input, and he gives me f, whatever the rule of correspondence of that function is, he gives me f of x plus delta x. Then the difference between them will be the change of y. So you can see that, huh? I hold it for a few seconds before. Now, this will be the algebraic setup for this pictorial demonstration. All right. Now, let me go to the next one. So next one, again, I'm using graphs as a geometry to give us as a visual aid to set up the corresponding algebra that and corresponding analytical form of it. So here I select let's say a sequence of points to the right of a fixed point, because the differential calculus deals with individual single points and investigate about the rate of change of that function at those particular points. So here I select that fixed point to be x1, then I give x1 to my function, and the function gave me f of x1. So this is the point, the fixed point. Then on one side, I repeat myself, on one side of this fixed point, I select a sequence of points. Now, the reason I hesitate and I hold my word for a few seconds, I say fixed to the right, because I will be explaining why I didn't say both sides of it. So right now we have a few points, and then we connect each of these points one at a time to the fixed point. Now, the line segment that connects 2 points in the on a graph, there is a special name for that. They call it secant line. Secant line. So we get a sequence of secant lines. Then what we do with those, we organize. In reality, we are collecting data. Then we organize those data in a we organize those data in a chart or in a table, and then we look at the table to see if we can notice any kind of pattern or any kind of information to come out of it. So this concept of geometrical interpretation that I'm using will lead us to the tangent line here, tangent line. And then the corresponding algebra and analytical will set up for us the formula that we are interested. So let me read this one for you. In order to determine the slope of the tangent line at the fixed point x1 f of x1 on the graph, what do? We select a sequence of points one side. Again, I'm repeating that because you may ask the question that why did you say one side? Because a secant line is a line segment that connects two points. So why not the other point to be the other side? That is still called secant line. Then approach those 2 points closer and closer to the tangent, to this point that we are interested to find the tangent line to this graph at this point. So we come back and answer that question. That's a good question, in fact, to ask. Okay, then I don't have to repeat, to complete that one is written, and I think is, I have checked the video, they are kind of large enough to visible for you to take notes if you are interested. Okay, now let me go to the next, if I may. Now, oh, by the way, let me just draw them so that just for the sake of it, I've done it over there. I have the pen here by now. And this is the secant line. The secant line is a line that connects two distinct points on the graph. So this will be my secant line for this point. So this will be the secant line for this point. And each secant line, because it's a line, they have, we can measure the rise over run for them, delta y over delta x for each of them. And again, I repeat myself, this is collecting data. So we collect those information, we put them in a table, and then seek for pattern or what, or information that lead us for continue further. And what I'm really saying is extremely important is in every branches of science. In every branch of science, we collect data, then we interpret those data, we organize those data, we put them in a chart, and then we look for pattern and information. So we are really doing that here in that regard. Okay, now next one, I don't know if I need, well, why not, I put that one up. So the next one is I already mentioned it, but just to repeat one more time, because repetition is a good process of learning, especially for beginner students, to keep repeating and repeating. Okay, here I already mentioned, this is my L1 that I connected this point to the fixed point. So I measured a slope of that, rise over run, and keep record of that, keep a record, and so on. And after that, this information that I get from this as a visual aid, I transfer them to their corresponding algebraic form. And the corresponding algebraic form of this will be this one. For example, for the first one, L1, will be f of x1 plus delta x minus f of x. Hopefully you know what is going on. Divided by delta x. And delta x in reality is x1 plus delta x, which is the second point, like for example x2, and then minus x1, because x1 and x1 they cancel each other, so we are left with delta x. So remember, delta x here again is x1 plus delta x minus x. Is exactly what we did for the numerator, the change of y. We are doing the same thing for the change of x. You follow me? And from this, we come back, we do it for the second point, secant line, and we find the slope of that, and so on and so forth. We do maybe 5, 10 of them. I'm going to do that, in fact, for the coming lectures. All right? And then at the end, we go to the calculus takes over. And the calculus goes to the limit that we cannot go, that, as I have already mentioned, is the word of the midgets, is the word of the points, and only mathematics can go into that. And by doing that, pictorially, graphically, we end up with the tangent line. You see that? We end up with the tangent line. Now we are going to generalize this one now. We are going to generalize. Instead of using individual fixed point like x1, f of x1, we are going to use x. So let me, what I mean by that. Now, this time I selected not x1 or x2, let xi to be any individual point on the x-axis, all right? So you're familiar with that, f of xi plus delta x minus f of xi over xi plus delta x minus del xi. Again, these two, they cancel each other, we are left with delta x. And that becomes hard, that as delta x gets smaller and smaller, as I already demonstrated that geometrically, pictorially. Now, then this, next time what we do, we are going, let me cover this one so that it doesn't get into your eyes and say what I mean about that. Next, instead of taking x1 or x2 or any particular point on the interval, instead of taking a particular point on, we select let x be an arbitrarily point in that interval. Arbitrarily point means what? Means if it is true for that particular arbitrarily point that we selected, should be true for every other points in that interval. And every other, we know that there are infinitely many of them. So instead of xi, next I select x. So again, x represents what? Every single point in that interval is arbitrarily is a representative. So whatever is true for x will be true for every single individual point in that set. That's what x stands for. So when we do that, look what happens at the end of the interval. I have written that, and I can take this one out. Now, then I go to generalize that one. Again, I repeat myself, x is an arbitrarily bought value, an arbitrary value on the x-axis, on the interval, on the given interval. So I write this one, f of x plus delta x minus f of x over what? X plus delta x minus x, which x, again, I keep repeating, is an arbitrarily point on the interval. Then, after this is, right now we set it up algebraically. And we do algebraic manipulation, we simplify that, and then at the end, the calculus takes over. And when calculus takes over is when delta x approaches 0. And then this approaching 0 will take us to the what? To the midget words, to the infinitesimal word. Which again, I keep repeating, that a word that we cannot go, only mathematics can go. And then brings out for us a very fascinating explicit function that we call it derivative. Okay, then the last one that I have to put is what I have already mentioned. We just go over that one more time. Okay, in this one, the limit of f of x plus delta x minus f of x over delta x, this limit now becomes a definition for us. And that is what definition of derivative comes from. Because this is the one gives us derivative. So we apply this definition to any given function, and then that function will give us what? Will give us out a derivative of it. So this limit can be interpreted as a derivative of the original function analytically, by analytically meaning that will be derivative of a function, and by geometric meaning this definition means a slope of the tangent line. Geometrically I have written for you. So this can be interpreted as what? As two meaning. Analytical meaning of that is an explicit function that we call it derivative, and geometrically it means a slope of a tangent line at any given point x. So I have written that one. Okay, then let me zoom this one up and say a few more words, and I close for today's lecture, if I may. Okay, then for the next lecture, I'm going to discuss about integral calculus. Again, I'm waving my hand. I'm not very rigorous in my in the words that I have selected. Each of them, they may have their own. There are many undefined in reality what I have mentioned in my words. But I will be diving deep into them and make it more explicit, especially with some good examples. Now, as the time, I guess we do have a few more minutes. I would like to say a few words about the history behind that. Now, the concept of integral calculus was known to man thousands of years back. But the concept of the differential calculus is new. It is in the late 17th century, and it was in a sense discovered by Leibniz, a German mathematician, and Newton, which was a British physicist. And there is a story behind that which is funny in reality, but it's true. Leibniz published his fundamental theorem of calculus, so the credit in reality should go to Leibniz. But then British start to say that Newton was already aware of that. And there was a big dispute between these two countries. For about a century, they were fighting with each other and arguing. No, it is the Newton who discovered it, but then German says, no, it was Leibniz. It is really ridiculous. It's ridiculous in a sense that they even accused Leibniz for stealing the idea of fundamental theorem of calculus from Newton. So it is funny because how in the world Leibniz could travel from Germany to go to England, to go inside the office of Newton, take his cell phone, take picture, record the picture of all his document, and come back to Germany and then publish the paper. It is indeed a joke, but this joke was very serious joke because there was a big dispute. I'm glad they didn't go to war because that's so childish argument to make. But anyhow, to my little knowledge of history of mathematics, I give the full credit to Leibniz. Okay, then I thank you very much for watching. I hope that my lectures are beneficial. I'm not doing that for any income or any money, but for the service of general service of students, and hopefully, inshallah, soon I get a position, some good institution that I can use their facilities and be a little enhance my presentation. Okay, then I thank you again for watching, and I wish you all prosperity and good health, and please stay and remain safe. So long.